I'm gonna hold your hand when I tell you this. You are misinformed about Fibonacci spirals. If you've ever heard someone say, the Milky Way is a Fibonacci spiral, and the Nautilus shell is a Fibonacci spiral, and my dog taking a shit is a Fibonacci spiral. No, I'm so sorry to break it to you. There's no mysticism about it. These are rigorous mathematical properties. The secrets of the universe that's held within logarithmic spirals is just the concept of self-similarity. That's the property they have. So the Fibonacci spiral is a discrete approximation of the golden spiral, which is a member of the family of functions known as logarithmic spiral. Like, all of these are in the family y equals mx plus b. They are linear functions, right? The parameters that you can tweak to make them different from each other are m and b. In the same way, logarithmic spirals is a family of functions. It's a polar function, but a and b are the two things we can tweak to make those graphs different from each other. So if you adjust b, it's like how tightly coiled that function is. And then if you adjust a, it's like scaling it up and down. It's literally multiplying the function by a bigger number if you increase a, right? But the cool part about log spirals is that when you multiply them by a bigger number, they don't get bigger, they just rotate because they're already infinite. That property is known as self-similar or invariant underscaling. Basically, if you rotate a bunch of them, you're gonna get stuff that starts to look like a galaxy. They're all self-similar. And we know that because you can just pack them all up. That property could be from any logarithmic spiral. I haven't even told you about the golden ratio, much less the golden spiral yet. Now we can move on to understanding the golden ratio. It also has self-similarity. So we have these distances, right? We have a bigger part and a smaller part, and together they make the whole. Is there a way that I can have the ratio of the whole to the big part be the same as the ratio of the big part to the smaller part? I'm gonna just replace these with variable names, but blue plus red is the same as the whole. That's how we got from here to here. If we can do that, then whatever ratio that is the golden ratio. Also written as 1 plus the square root of 5 over 2. Also written as 1.618 irrational nonsense. Okay, now I'll actually draw a Fibonacci spiral for you. Suppose you draw a square of side length 1, and then you draw another square on top of it, also of side length 1. Together, this makes side length 2. And we make another square, and now we have 2 plus 1 is 3. And then we make another square, and now it's 3 plus 2. So we make a square of side length 5. Well, you've done that infinitely many times, perfect. This is how we start. Quarter circle here, quarter circle here, quarter circle here, quarter circle here. You just do that theoretically infinitely. For the sake of preserving space, I'm gonna stop here. As you do this to infinity, the ratio of the smaller side to the larger side is the same as that, which, if you recall, was the golden ratio. But I got to the 1, 2, 3, 4, 5, 6, 7th entry in the Fibonacci series. The short length is 8 units wide and the long length is 13. So because I stopped here, this would be my approximation for the golden ratio. I'm not too sad with that, you know, that's pretty okay. That's how this relates to this. Okay, now that I've told you that, Fibonacci spirals suck, dude. The curvature here is for a circle of radius 1. It immediately jumps to the curvature from a circle of radius 2, and then it immediately jumps right here to a curvature of a circle of radius 3. And the curvature keeps discretely changing at all of these points. That's cringe. I don't like that. What if there was something that preserved these properties while having continuous curvature? That's what the golden spiral is. We can preserve this property by solidifying it in some math here. So what we're saying is the radius of the current angle plus 90 degrees, so like the next radius, is equal to phi times the current radius. Unfortunately, degrees are dumb and stupid, and this should be pi over 2 radians. The golden spiral is a member of the logarithmic spiral family, which is described thusly. If we plug in theta plus pi over 2 into here, we get r of theta plus pi over 2 equals a e to the b theta plus pi over 2. And then we could write this side as phi times a e to the b theta, and then the a would cancel out, and the e to the b theta would cancel out. And then we're just left with e to the b pi over 2 equals phi. Again, we know this, so we're actually solving for b here. So if we were to plug this b into there, because a doesn't matter because all of them are self-similar, a just rotates whatever we put in here. That is the equation for, you can simplify it more, but that's what the golden spiral is. Can we check if the construction has continuous curvature everywhere? Look at him go. The circle is continuously increasing in radius. Isn't that awesome? It's not jumping discretely. That's why it's called Fibonacci sequence, because it's a lie. Plants aren't programmed to grow in a way where only discretely every 90 degrees they have a seed or something, right? Their genes just kind of code them to start producing things, and it happens to have the property of self-similarity, and that's why it crops up in nature all the time. The only thing that's specific to the golden ratio, though, out of the family of logarithmic spirals, is that from any angle, if you go 90 degrees from it, then it's going to be phi times as far from the origin, or the radius will be phi times as bigger, or the golden ratio times as big. All logarithmic spirals have that effect, but it just won't be the golden ratio. It's just the fact that it's a golden ratio, and you can construct something nice like this from integers starting at 1, 1, 2, 3, 5, 8, 13, whatever.